Hello everyone. Today's lecture is about exponential Fourier series, where in the last previous lecture we learned that complex exponential signals are orthogonal to each other. Okay, so in the previous lecture I told you that the exponential j m omega 0 t and exponential function j n omega 0 t are orthogonal functions. They are orthogonal functions. They are orthogonal functions over the given interval for any integer values of m and n except m is equals to n. Okay, so whenever these two exponential functions are orthogonal functions only when it is m not equal to n. Okay, they are said to be orthogonal function except at m equal to n. Clear? So that is, according to this concept, we can say that is all the integer values, for example starting from 0 e to the power j 0 omega 0 t comma e to the power j 1 omega 0 t comma e to the power j 2 omega 0 t, so on for the positive value of n, and also for the negative value, for example minus e to the power minus j 1 omega 0 t comma e to the power minus j 2 omega 0 t, e to the power minus j 3 omega 0 t, and so on. These all are orthogonal. Within the interval t0 to t0 plus capital T. t0 to t0 plus capital T. So by knowing this fact, we can say that any periodic signal x of t in the given interval t0 to t0 plus t can be represented using these mutually orthogonal complex exponential signals. That is, any signal x of t, can be equal to it can be approximated using these complex exponential signals by writing with the coefficients like c0 exponential j 0 omega 0 t plus c1 exponential j 1 omega 0 t plus c2 exponential j 2 omega 0 t, so on. Similarly, we can also write c minus 1 e to the power minus j omega 0 t plus c minus 2 e to the power minus j 2 omega 0 t, and so on. By looking at this series expansion, we can write within a summation symbol the formula of exponential Fourier series. So erasing this page and writing the formula of exponential Fourier series is equals to summation of n equal to minus infinity to plus infinity Cn e to the power j n omega 0 t. So this is the formula for exponential Fourier series. All right. Now from this formula, we need to know what is Cn. Cn is known as the exponential Fourier series coefficient. Cn is known as the exponential Fourier series coefficient. So from this formula, now the part we want to evaluate is the evaluation of the coefficient Cn. If we know the evaluation of coefficient Cn, we can add in this formula and we can write the exponential Fourier series and by substituting different values of n. So hence this Fourier series, exponential Fourier series is very, very important topic in your syllabus where it is mostly widely used form of Fourier series and where the calculation of the exponential Fourier series coefficient also is easy. So now next topic in our portion is determination of In the previous section, we discussed about exponential Fourier series formula, from where we know the formula of exponential Fourier series is given by x of t is equals to summation of n equal to minus infinity to plus infinity Cn e to the power j n omega 0 t, where omega 0 is known as the fundamental frequency given by 2 pi by t. 2 pi by t, t is known as the fundamental period. To determine the coefficient Cn, we need to find out the formula of Cn. So to do that, we need to multiply both sides of this above equation by the factor e to the power minus j k omega 0 t and integrate over one period, that is, we can tell that period is t0 to t0 plus capital T. Okay, by integrating within this period, after multiplying both sides, we get integration t0 to t0 plus t x of t into e to the power minus jk omega 0 t dt is equals to integration of t0 to t0 plus t. Then the right side will write it in the bracket summation n equal to minus infinity to plus infinity Cn e to the power jn omega 0 t, and that right side also will write multiplication e to the power minus jk omega 0 t and dt. So this is by multiplying both sides by e to the power minus j k omega 0 t and integrating over one period. Now, since in the right hand side there are two exponential functions, they are multiplied. So we can say these two exponential functions are orthogonal to each other when the value of n and k are not equal. If n and k are not equal, they are called as orthogonal functions. Okay, so by doing that, we can rewrite this right hand side as so again I'm writing from the left side also. So integration of t naught to t naught plus t x of t e to the power minus j k omega 0 t dt is equals to, we'll interchange the summation and integration. By interchanging the summation, summation comes before, that is summation n equal to minus infinity to plus infinity Cn, and then I can mention the integration t naught to t naught plus t, that is exponential. First function is exponential j n omega 0 t, and the second function is exponential minus j k omega 0 t dt. So since these two exponential functions, if you say if n is not equal to n is not equal to k, that is they are orthogonal. That means, that is, we can say that integration of t naught to t naught plus t e to the power j n omega 0 t into e to the power minus j k omega 0 t dt is equals to 0 for the value k is not equal to n, for k not equal to n. Okay, and if the value is n equal to k, the integration will be t, because the multiplication will be 1 and the only integration will be of dt. So dt integration is t. So this is for the value k equals to n. So considering that, we will just determine that, assume that k is equal to n, remaining all, whenever k is not in the range of n is equal to minus infinity to infinity, whenever n is equal to k, then only this integration is, that is value is t. For remaining all value of summation for any value of n, taking from minus infinity to plus infinity, the integration is 0. So hence the right hand side integration result is the capital T. It is equal to T. So by substituting this result of integration as T and writing in the right hand side, and there is no more summation we have to write, because there is only one value we have to substitute, that is n equal to k. Remaining all value is 0. So hence, writing that in the right hand side, integration of t naught to t naught plus t x of t e to the power minus jk omega 0 t dt is equal to Cn into t. Or else we can, in place of Cn, we can write, in place of n, you can write now, because you have substituted n equal to k, we can write ck. Okay, Hence the Ck is the formula of Fourier series coefficient, exponential Fourier series coefficient given by 1 by t integration t naught to t naught plus t x of t e to the power minus jk omega 0 t dt. Or we can also write the formula as Cn is equal to 1 by t integration t naught to t naught plus t x of t e to the power minus j n omega 0 t dt. Hence this is the given formula of the exponential Fourier series coefficient. This is the formula for exponential Fourier series coefficient. This Fourier series coefficient Cn will have discrete spectrum because Cn will exist only for discrete value of n. So hence by drawing this Cn, we can say this Cn representation is called as complex spectrum, which has both magnitude and phase. So following point may be noted that from the Cn we can draw the magnitude line spectrum, which is always an even function of n, and also phase line spectrum, which is an odd function of n. So this we are going to discuss more in detail in the next class. Thank you all.